Welcome to week 3 of Machine Learning Foundations. In this week as well as subsequent 3 weeks, we'll be looking at topics in linear algebra, specifically those that apply that would be helpful in understanding machine learning. We'll start with the first lecture today, which will be recap for some of you and maybe new for some. The idea is to understand 4 fundamental subspaces associated with any matrix, which is namely column space, null space, the row space and the left null space of a matrix. We'll be defining these 4 subspaces and then try to calculate them for a given matrix and try to understand the relation between the dimensions of these 4 subspaces and how they relate to the number of rows and columns of a matrix. Okay, we'll start with a recap today. We'll be looking at the 4 fundamental subspaces for given matrix A. First one is column space, let's say C of A. Now, for simplicity, suppose A is this matrix with columns U1, U2 until Un. So, these are the columns. Then the column space of A is the span of these columns, which is all linear combinations of the vectors U1 until Un. And column space has connections to solving Ax equals B, as you know. Yeah, so if I want to look at solving Ax equals B, then column space plays a role. For example, one could ask the question, for what B does Ax equals B have a solution? And the answer is for all B belonging to the column space of A. For example, let's look at an example. Suppose you take the matrix so Ax equals B is solvable for B belonging to column space of A. The question is, does every vector in R4 belong to column space of A? The answer is no. Some vectors in R power 4 are not in the column space of A because what you have is you have 4 equations in 3 unknowns. That's what we have. We have 4 equations in 3 unknowns. Let's put it this way, because Ax equals B is 4 equations in 3 unknowns. Anyway, for this example, for the example above, if you observe column space of A, if you observe column 3, it's just column 1 plus column 2. So, column space of A is span of column 1 comma column 2 implies column space of A is a two-dimensional subspace of what? Of R4. Hope this is clear. Now we'll go on to the very next page. So just a quick recap. So column space is a set of all linear combinations of the columns of a particular matrix, and that plays a role because you want to solve Ax equals B, and if you want to know for what B this is solvable, then B has to be in the column space of A. And we just saw an example where every B, every possible four-dimensional Euclidean vector is not in the column space of this matrix. Now the very next subspace which is important is the null space. So the null space of A is the set of all x such that Ax equals 0. Now why is it a subspace? Why is n of A a subspace? It is a subspace. I mean, what are the two conditions that you want to verify? Let's say if you take two vectors, let's say x1 and x2 both belong to null space of A, then Ax1 equals 0 and Ax2 equals 0 implies A of x1 plus x2 equals 0 implies x1 plus x2 belongs to the null space of A. Now that's the first thing. The second thing is, suppose you have a vector here, then what is A of alpha x? Alpha is a scalar. Is alpha times Ax equals 0. So alpha x also belongs. Hence n of A is a subspace. Now let's look at an example. For the same matrix A, so recall this matrix. So A is as before, which is say 1, 2, 3, 4, 1, 1, 1, and 2, 3, 4, 5. I would encourage you to pause the video at this point and figure an x such that Ax equals 0. So find an x such that Ax equals 0. So the point is, if what I want, that is equivalent to saying a linear combination of the columns of A should result in the 0 vector. The 0 vector. Now what would be a valid linear combination? We know that column 1 plus column 2 is column 3. So if I add up first two columns and subtract the third column, I would get the 0 vector. So 1, 1 minus 1 belongs to null space of A. Got it? And so you have to understand the dimensionality here. So null space of A is a line in R3. So you're looking at columns of A, and there are 3 columns in this matrix A, and you're looking at linear combination. So every entry in the null space belongs to R3. Yeah. And now the question is, does it span entire R3? No, it's just a line. This is all you get for the null space. Yeah, just a quick remark. if A is invertible, then null space of A has only 0, and also column space of A is the whole space. Yeah. If that is not the case, then I mean, and obviously, if column space of A is the whole space, then Ax equals B has a unique solution. Yeah. Yeah. In this case, Ax equals B has a unique solution. Else, null space of A has some vector, let us say xn, that is non-trivial, it is not the 0 vector, and Ax equals B solutions can be written or of the form x equals xp plus xn, where Axp equals B and Axn equals 0. Yeah. Okay, so much for the null space. Mark 2. Can use Gaussian elimination to find the null space of a matrix A. That is, you solve Ax equals 0. That's what you do. Yeah. I mean, I hope everyone has done Gaussian elimination before this. Please go back and revise. For the sake of illustration, I'll just give you an example without going through all the steps in detail. Suppose you have the matrix say 1, 2, 2, 2, 2, 4, 6, 8, 3, 6, 8, 10. And then you do Gaussian elimination. What you would get is 1, 2, 2, 2, 0, 0, 2, 4, 0, 0, 2, 4. And some more steps would lead to 2, 2, 2, 0, 2, 4 and 0, 0, 0, 0. So now if I want to highlight the pivot columns, this would be it. Pivots. Now if I take this matrix, let's call this matrix U, call this U, then solving Ux equals 0 is simple enough. Which is like saying 1, 2, 2, 2, 0, 0, 2, 4, all zeros, 2, x1, x2, x3, x4. You want this to be so as I highlighted before, column 1, column 3,
pivot columns and column 2, column 4 are the free variables. And here is the procedure. The way you go about figuring this is you take this free variables and set them to basis entries. So x2 equals 1, x4 equals 0. If you do this and if you solve the system, what you get is 2x3 plus 4x4 equals 0, which implies, and also x1 plus, which implies x3 equals 0 because x4 equals 0. x1 plus 2x2 plus 2x3 plus 2x4 equals 0, which implies x1 equals minus 2. And that gives us a first null space entry, which is x1 equals minus 2, x2 equals 1, x3 equals 0, x4 equals 0. This belongs to null space of A, but this is not the only one. There are two free variables. So what you have to do is, now the alternate choice is to set x2 equals 0 and x4 equals 1, implies what you would get is 2x3 plus 4x4 equals 0, which implies x3 equals minus 2. So you can pause the video and work out these on your own. They're fairly straightforward. And then if you write down the other equations, x1 plus 2x2 plus 2x3 plus 2x4 equals 0, this would imply x1 minus 4 plus 2 equals 0, which is the same as x1 equals 2. And that gives us the second entry. So the other entry that belongs to the null spaces, let's call this U. The other entry is, we say 2, 0, minus 2, 1 belongs to null space of A, which is, so the bottom line is null space of A is the span of U comma V. Now this quantity rank you might have learned before. So the rank is the same as number of pivot columns, okay. In the example above, rank of A equals 2, and the nullity is the number of free variables in the example above. Nullity P equals 2. Okay, so rank equals dimension of column space of A, nullity equals dimension of null space of E. If A has n columns, then rank plus nullity equals n. Which is equivalent to saying rank of A equals R, the same as, okay, let's erase this. Nullity of A equals n minus R. So this is the rank nullity theorem. I hope things are clear. I will not delve deeper into this, but I hope students have got a reasonable idea of the rank of a matrix and the nullity of a matrix, and how to go about finding it. In particular, the underlying subspaces are the column space and the null space. So these are the quantities that are important. The other space is the row space. The next space that you have to look at is row space, and this is nothing but the column space of A transpose, which is the space, or equivalently, span of rows of A. So R of A is equal to column space of A transpose. And the important fact is this, call this important fact. This goes without proof. We have seen this proof before. Column rank equals dimension of column space of A. Row rank equals dimension of the row space, and the important fact is column rank equals row rank. So far we looked at column space of A, null space of A, and also row space of A, which is equal to column space of A transpose. So you can guess the very next space that you are going to look at, which is the null space of A transpose, which is called the left null space. Which is null space of A transpose. So which by definition is a set of all y's such that A transpose y equals 0. Or equivalently set of all y such that y transpose A equals 0, which is like saying that if I want to, if A is a m cross n matrix, for a m cross n matrix E, what you are looking at is y1 until ym multiplying E, and you want this to result in zeros. So looking at a linear combination of rows that results in the zero entry. So this is like saying a linear combination of rows leading to 0. But okay, so that's the left null space. I'll probably look at another example again to illustrate this 4 subspaces. Yeah, please pause and go back and look at the definitions carefully if you are encountering this for the first time. Now a remark. Yes, I'm crossing matrix. Now dimension of column space of A plus dimension of null space of A, we know is the number of columns, is the number of columns of A, which is equal to n, which is like saying that R plus n minus R equals n. Now if you apply the same to A transpose, what you would get is dimension of column space of A transpose plus dimension of null space of A transpose equals the number of rows. And that is M, but we know dimension of column space of A transpose equals the rank, implies R plus dimension of null space of A transpose equals M, which implies dimension of null space of A transpose is M minus R. I mean, if you look at, for example, let's take a simple example. By hand we can calculate this without going through Gaussian elimination. Imagine A is 1, 2, 2, 2, 2, 4, 6, 8, 3, 6, 8, 10. Then I want a linear combination of the rows. What I want y transpose A equals 0. So I would encourage you to pause the video at this point and figure this y. I'm going to give out the answer. The answer is, you can say that the third column is just the sum of the first two, and so this is the solution. Okay, I am going to do another example, much simple, just to make all these spaces explicit without going through Gaussian elimination. Say 1, 2, 3, 6. So M equals N equals 2. What's the rank? So the first thing, what is the column space of A? If you look at this, pretty simple. The second column is just 2 times the first. So column space of A is just the line through 1, 3, implies rank of A equals R equals 1. What is the null space of A? What is one entry that belongs to the null space? So pause at this point, again figure this null space on your own. I'm going to give out the answer. So if I take minus 2 times the first column and 1 times the second column, that would belong there. There won't be any more linear independent vectors because rank of A is 1 and there are 2 columns. There's just one more entry left. So this is the line through minus 2, 1 implies nullity of A equals N minus R equals 1. Now for the same matrix, what is the row space? Is equal to column space of A transpose, and this you can see, just go up a little. Again, it doesn't change much. It's a one-dimensional quantity. Line through 1, 2. Again, dimension of row space of A equals R equals 1. Now you are left with the left null space, which is null space of A transpose. This you can check is the line through. And through what? You just look at this, the answer will be apparent. Minus 3 times the first row and 1 times the second row will give you the 0 entry. Dimension of null space of A transpose equals 1. Now I would give you folks a homework here. Homework, work out the 4 fundamental subspaces, which is column space of A, null space of A, column space of A transpose and null space of A transpose for the following matrix, which is A equals. You'll have to do Gaussian elimination, do some work, reduce it to the row echelon form, and then things will be apparent. So this is your matrix.
Okay, so a quick recap before we end this lecture. So in this lecture, what we did was to understand what the 4 fundamental subspaces associated with a matrix are, and these are the column, null space, row space, and the left null space. What we did was to understand how the dimensions of these relate. In particular, if you look at, the dimension of a column space is the well-known quantity, which is rank, and dimension of the null space is the nullity. And if I add these two numbers, which is the rank and the nullity, we would get the number of columns. And on the row side, you have the dimension of the row space, which is also the rank of a matrix, which is a well-known linear algebra theorem. Dimension of the row space is the column space. But if I add the dimension of the row space, which is the rank, and the dimension of the left null space, then I would get the number of rows. This are the two things. And then we looked at an example where we worked out, we characterized the 4 fundamental subspaces by taking a simple enough matrix, and we understood what their dimensions are, and we characterized them by providing the basis.